All right, so we are starting. Very sorry. Innocent was supposed to lead this, but unfortunately, something came up, and then I had to step in as an emergency facilitator. So kindly forgive me if the preparation didn't go as well as it was last time. All right, thank you. So today, this is the second series. Um, the second part of our webinar series that focuses on the subgroup analysis and the meta regression and publication biases. So without wasting much time, as I also have other meetings coming up. So I'll share my screen and then we can begin right away. Share screen. Okay. All right. Slideshow. Slideshow from beginning. Can you all hear me? Can you all see the screen? All right, good. If you can see the screen, let's move on. All right, so like I already said, this is focusing on subgroup analysis and then publication biases. This is going to be more of like a short theoretical introduction like I did the last time. And then we do like practical demonstration, a short practical demonstration as well. Not it's going to be that comprehensive that it meets all your needs, but at least it does give you some overview of how these are done. I'm not really conversant with the graphic user interface ones like Stata and the other ones that you can simply click. So normally I use the R language, which I believe is more flexible. The results that you end up getting in R is the same else everywhere. So it's just a matter of understanding that these are what the values mean, and this is how to run them. And then later on, if you are using Rayman and Stata or any other software like JASP or Jovi, you can easily do it. All right. So publication biases. This is defined by Rostein. I think there is also one that I've not cited his work. Okay, he's also here, Borenstein. So I have registered for some of the what do you call it, the software licenses, which is currently chaired by him. If I may remember well, Borenstein is well-noted meta-analytics who is part of those developing a comprehensive meta-analysis package, CMA. And he has worked extensively in various aspects of meta-analysis, from introductory sessions to dealing with publication biases to dealing with other technical aspects of the meta-analytic process. And he and his colleagues, they give this explanation that publication bias exists when the probability of study published is affected by its results. What do I mean by this? Let me give a very simple scenario. The last time I used an example of a pharmaceutical company like Big Pharma. So there was some time ago where antidepressants was a very important thing in dealing with some people who are suffering from mental health issues. And as you all know, antidepressant companies are multi-billion-dollar companies, especially those of us in US know best. The medical companies are multi-billion-dollar companies. And normally these companies, not all of them are complying with our safety as people because they are profit-oriented people. They are profit-oriented companies. So sometimes a drug may not be that effective, but whichever way, they still find their way through. How do they do that? So I use an example of one case where antidepressants were released to the market. And then after some years, they had to assess the effectiveness and all that. And Technically, this company employ or gave the contract to some medical researchers who had to conduct a meta-analysis to validate, to check how effective these particular antidepressants were to solving these problems. So when this thing came out, they reported positive results. And it only showed like the medicine or the drugs that they brought on board were effective to their patients. And that gave in a lot of market. Some years, other meta-analysis also came forward, and then they also questioned the results. And what they did was they went to the CDC and then I think the NIH, because if the government is funding a company, then anytime you generate your research, you have to report the raw findings or the raw data back to those particular institutions like the National Health Institute, National Institute of Health, or CDC, the US Center for Disease and Control department. So when the I can't hear you anymore. Can anybody hear me? Who can everybody hear me? Okay, all right. I don't know why the other person is complaining. I don't know. Maybe please check your speaker. Maybe something wrong with it. All right, so I continue. They reach out to this particular NIH, and then they got the raw data that was used in deriving what do you call it, some of the randomized control trials and the other papers that are not published, but they are kept because those ones were those that did not report positive results. So they didn't publish them. They kept them as raw, white, gray materials. Then these researchers reached out to them. They collected all these papers, the both published and unpublished ones, and then they reanalyzed the data. They did a meta-analysis again. And then they realized the standardized mean difference wasn't that huge. And in fact, the p-value wasn't significant. And if it was just purely by chance. And that casted a lot of doubt, as in what the other people did previously. Did they dubiously selected a few studies that reported the positive findings and then pulled the effect and then told us, the whole world, that this was a good drug? Yeah, so that was where the issue of publication biases begin to take place very significantly in the academic domain. You know, like we have to check in this one very carefully, because the cost of publication biases can be too huge. A drug that may kill people because of publication biases may report that it saves life. Some results, some drugs at all shouldn't get onto the market, but because of publication biases, they end up getting there. So as practitioners and as those who are interested in medical research, these are very critical areas that even after this particular webinar, you have to dedicate a lot of your time understanding it in detail so that you don't fall prey to it. Because for all you know, somebody may come to validate your work, and then somebody validate it and you are wrong. You know the consequences of it. They retract it. They retract the paper, and that becomes a dent on your image. And sometimes they may even end up firing you from your university if you're a professor. So please take it seriously. All right. So how does publication bias come in? The last time, if you remember, I talked something about file drawer problem, where you selectively draw out certain studies and leave out others. Because we know, of course, we cannot get all the papers that are published out there. I can't show you, okay, these are 100 papers that are all the papers in the world that report on, let's say, the effect of COVID on mental health. We can't be sure that these are all the papers, but statistically, we want to be able to say to some extent that even those that were left out by random chance, but not systematically, that intentionally were left out by intention, like because they didn't report the results that were expected, or they reported in different languages, or whichever way the case may be. We just want to prevent file drawer problems that are not driven by random chance, but systematically given out. Now, how do we deal with them? We have to first of all look at the search strategy. Are we comprehensive enough in our search strategy, said that we are not eliminating certain credible studies as well? Because not all studies really end up getting the visibility that they need, especially if they didn't report the results that people expect. They may not end up getting the visibility that it needs. So if you are searching and your comprehensive search, like your search isn't that comprehensive, then it becomes a problem. Is everyone seeing my slides? Hello, please indicate. Yeah, so those who are not hearing, who are not seeing the slide, please check your machine again. All right, so I'll move on. So you check for the your search strategy very carefully and make sure that all the parameters that are necessary are well defined. And sometimes we all fall prey. Sometimes we all fall prey to some of these issues that will end up drawing studies and living out on the basis of language. And then I'm also a corporate of that. Sometimes we just realize that I'm searching papers in Africa, but then because we do not have French like proficiency, we may end up leaving out certain studies. But of course, now ChatGPT and other technology are making it possible for us to still use French related. So now I don't think language barrier is really a big problem. That should prevent you from dealing with these particular biases. All right. So I move on to including also some great literature. I gave an example of antidepressants paper that became one of the biggest controversy in the biomedical field. If they had left out the unpublished studies, it would have made to the public that the drug was effective. But these studies were, those that were not published, were done intentionally. They were suppressed results that didn't get out there. And that is also goes out to make sure that some of the great studies are supposed to be included with carefulness. Scrutinize it carefully and then make sure you include them and run some sensitivity analysis to see if the results will change or not. And then the other ones, provided you believe you have done your comprehensive search, you have included great literature, there is that likelihood that we may still be leaving out certain studies systematically that without even our notice. So we still have to find a way of detecting those ones. So we have to find a way of detecting them to know that, oh, there are some publication biases that we need to be careful of. Or when we are reporting to our potential readers, we make them know that, oh, this is a study, we reported publication biases. Even though the study is important, we believe those who are reading it should be very careful in the way they generalize the findings. All right. So moving on to the types that are available. So many years ago, over 3 decades ago, they used to have something we call horizontal fail safe N. So those who are using open meta, I think the earliest one that I used did not really have some of the advanced current publication bias detective functions. So the Rosenthal fail safe N test actually was available. It's still not, it's not recommended. I wouldn't want to talk even about it when the other ones are available. Completely disregard it when you are, because it's not reliable at all. So there are other ones like funnel plots that is also used. Those who are got a chance to do their own meta-analysis would appreciate. So let me go to the publication. Let me use a funnel plot to demonstrate. Can you all see the funnel plot? Can you all see my distance? Can you all see the funnel plot? Please indicate yes. All right, good. All right. So you can see we have funnel plot, 2 of them, one to our right-hand side, one to our left-hand side. So technically, if there are no publication biases, the dot that you are seeing inside the funnel represent the studies that we have included. If we do not report any publication biases, then we should expect to see something symmetric, something that are funnel in nature, that almost all the studies are falling within the funnel bound. That is what we mean by there isn't any detectable evidence of publication biases. And then we also go to the right-hand side, where we have a similar publication by another funnel plot. However, not all the points are falling within the funnel. Some of them are outside it. Such a case, we can have visual, impression that there are some publication biases happening here. Why are we saying there are publication biases here? We assume that if we included almost all different kinds of studies that did not really rely on sample size, whether the study used small sample size, whether the study used big sample size, we included them, provided there was a scenario like that. We would end up getting something that was close to what I have shown in the left-hand side. Because from the last time I told you, standard error has an inverse relationship to the sample size. So the bigger the sample size, the smaller the standard errors. Therefore, the standard errors are going to be decreasing. So you see that we have included studies with large sample size. So they are reported at the topmost part. I don't know if you can see the topmost part of this funnel plot, like the way my cursor is showing. You can see some studies are there, somewhere around standard error 1 all the way to 0. You could see there are studies there. And when you come to the bottom of it, somewhere along 2.5, standard error of 2.5, you see two studies around there, which means that studies that are reported larger standard errors and those reporting low standard errors, all of them are included in our meta-analysis, which is good. So in that way, we didn't systematically left out small studies, because almost small studies are always going to report larger standard errors. That is the problem. Now, when we come to the right-hand side of the problem, we are seeing something very asymmetrical. Very asymmetrical. You realize that though the bigger ones, those with low standard errors, tend to cluster at the top. However, they tend to be relative risk ratios that are more negative than they are positive. So they are kind of a bit influenced. And also when you come to even to the down part of it, like around the 1.2 to 1, you'd realize that there are more studies reporting standard errors that are to the left aspect of our middle line. So our middle line is the 0. There are a lot of studies to the left-hand side of it than right-hand aspect of it, which is showing that even studies that did not report positive results are excluded. For example, if we expected that the higher or maybe distance was influencing my exposure to lead in a particular contaminated site, in that way I'm expecting negative results, like the relationship between how proximate somebody is to, let's say, lead acid abandoned site, a waste site, or something like that. So in that way, I'm expecting that the closer the person is to this dump site, then the higher the risk of getting this particular lead in the blood. Then the further, then the less the exposure. In that way, this kind of the distance versus the risk is inverse. That is what our hypothesis will tell us. But how about studies that reported positive? How about studies that reported that even the further you go away from the dump site, then the higher your risk? This is kind of counterintuitive. Now, when you send some of these kind of studies for publication, the editors and then even the reviewers are going to look at it like, this goes against the hypothesis all over. Now let's look at it. Is this results influenced by the sample size? Is it because he used small sample size? That is why he's getting these biased results? Yes, if only your sample size is less, then your study will be rejected, higher chance of being rejected. So it won't go anywhere. It may even remain only as a preprint. And that is what these particular pictures are showing. Are you following the logic I'm using to explain this? If you understand the logic, please indicate yes. Hello? Yeah, okay. We're all following, and that is good. So this is the simplest I can use to explain the publication biases. If you are reading it from the literature and they start quoting the equations, it becomes very, kind of daunting, and a bit discouraging to even continue with it. But this is the basic way you can understand about it. We don't want the asymmetry. We don't want the sample size to have anything to do with the study being published. And we don't want to also have an example of favorable results being the reason why the study is published. We just want to get studies that are independent of all these criteria so that we know we are not being biased towards anybody or any researcher out there. Very good. Now I can move on. Now, how do we, there are other ones. I mentioned Rosenthal's fail-safe end test, which is, I'm saying, discarded altogether. It's not necessary. Funnel plot, I have shown you how necessary it is, but it also, there are also other aspects like being biased. Of course, how statistically significant can my eye detect something that is extremely asymmetric? My eyes can only detect patterns, but it can't tell me quantitatively what pattern I'm looking at. Of course, we saw from the picture that the right-hand side of it, there are some points that are out of the funnel. But how do you know how statistically significant are these asymmetries? Our eyes can't answer this kind of question for us, which is why we need some form of statistical test to do these particular things. Then we have two basic ones. Of course, there are other ones I'll mention, but for those I have used eGuess regression tests, and I have used p-test regression tests. All of them are used in different scenarios. Now, what are the eGuess regression tests? We have the equation here, which is given as the theta, the hat theta k divided by the standard errors. What does this mean in the statistics? When you have your mean divided by the standard errors or the standard deviation, you're always going to get something called z-scores. Z-scores. And then if you guys have been doing a lot of hypothesis testing, you realize that the 95% confidence intervals or 5% confidence level is always related to 1.96, which is also an example of a z-score. So we want to say how statistically significant is our beta naught, which is the intercept. How statistically significantly different is it away from zero? Because if we divide our mean by standard errors, it may either be less than 1.96 or equal to or greater than 1.96. But then the more lesser it is away from 1.96, then it is moving towards zero, which means the relationship will become insignificant. If those of you who have been doing a lot of regression, multivariate regression tests, always check your coefficient. You see the coefficient, you see the standard errors, you go and see the z-scores, you see the t-test, and normally when you see that anything that is below 1.96 is always going to give a p-value less than 0.05. Probably from today, you can check those particular things and you can confirm it. So this example is something logical, something like something same that we are doing here. We want to say that, okay, provided we didn't have precision at all, because the beta naught plus beta I multiplied by 1 divided by the square, like the standard errors, which is the weight of the study. If we say, if you hold the beta 1 constant and then the beta naught, which is what do we expect to find in our Y if we didn't have precision at all in our studies? If the beta 1 was 0, that we didn't have any accuracy at all in our studies, what do we expect our z-scores to be like? Do we expect it to be close to 1.96 or less than 1.96? Who is this? My email address. All right. So that is an example of it. So the expected z-score should be scattered around 0. If we, because when the small studies with high precision will not actually overlap with the expected value of it, because we have an expectation. Our pool value we always have some confidence intervals around it. And if we had some studies that are small, we expect these particular studies to have very large confidence intervals. So it should overlap with our expected values. And if we have another ones that are also more of like small sample size, but then they have very high precision, it means the confidence intervals are very narrow. So it isn't that wide. That is all this equation is trying to tell you. If you don't understand it statistically, it's something telling you that if we didn't have accuracy at all in our studies, what do we expect to find in each of the studies? That is what exactly this one is trying to tell us. If there are no publication biases, normally you should see p-value more than 0.05. I wouldn't go much more detail into statistical philosophy here, but anytime you are dealing with eagerness regression test, always check for the p-value. If it is less than 0.05, then there are publication biases. If there are more than 0.05, then there isn't. That is a logical thing to think about. And normally, don't use the beta 1, use the beta naught, because we are trying to say that provided all these beta i's and stuff are 0, what do we expect the beta naught to be like? If the beta 1, the beta naught is 1, how statistically different is 1 from 0? It's all what we want to test. If there isn't statistically significant difference between beta naught and then 0, then it means that there isn't any publication biases at all. If they are statistically significantly different from 0, such that our p-value is less than 0.05, then there are some form of publication biases we need to be wary of. However, what I've reported here is normally good for the eagerness test. Is good for if you're dealing with mean values. How about when you're dealing with binary outcomes like risk ratios, odd ratios, and some form of proportional meta-analysis like prevalence? In that way, we cannot use the eagerness. I think it can't give us some aspect of it, but it's going to give us some biases. So what this particular, there's another one which is called PTES. It was developed by Peter and his colleagues, and they adjusted for this particular eagerness regression when you are dealing with binary outcomes like odd ratios or binary outcomes and stuff like that. So instead of using the mean of the K, which is the pool value of steady K, we take a log of it to normalize it. Because we understand that sometimes if you're dealing with binary outcomes, it can be some form of skewness. There can be some skewness in there. And if it is skewed, we cannot make very accurate inferences, especially using the z-score. So we take a log of it to normalize it, such that we can now report the results. So it's like a corrected version of the eagerness test. And then there are other aspects of it like Duval and Tweedle, trim and fill. So this is kind of a bit also old way of doing things. This is not necessarily detecting only the publication biases, but after we have detected, what do we do about it? Do we correct it or we leave it? That is where the Duval and Tweedle is coming in. It's trying to trim your studies and fill it in. So it generates, if I trim out study A, I fill it in with a hypothetical one with it, so that if all of them were skewed to the left, I kind of fill in the left aspect of it with the hypothetical values of the one that I excluded. In that way, when we run the final plot again, we end up getting something quite symmetric. These were what we were using olden days. Now people are saying it's not also safe because it is also influenced by, if you have very large heterogeneities in your studies, like I squared equal to greater than 50%, it isn't necessary and it isn't accurate enough. So we should be very careful about it. Then there are also other more recent ones, which myself I've never used, is something we call precision effect estimate with standard errors. So we are adjusting the precision effect. If we exclude some studies, how do we adjust those particular small sample effects such that we can have high precision? So we are basically adjusting it. Please, who asks you guys to give your email addresses? Anyways, let me continue. So these are some of the few ways that we can get the publication biases detected. Then I can move on. We have talked about this. Now let's talk about the subgroup analysis quite shortly. Then we can run some few demonstrations. So subgroup analysis, what are they? It's a form of way of detecting, provided the last time we talked about pool means. We have pool, okay, the overall effect of COVID-19 on mental health is this. We have the results like coefficient of 0.5. is this particular 0.5 influenced by certain factors like gender? Is it influenced by the country it is coming from? Is it influenced by the fact that the study was conducted in hospital setting versus community setting? Is it influenced by any other factors? We don't know unless we conduct a study. So anytime you, before you even start your meta-analysis at all, make sure all the necessary, you have some hypothesis in mind, and then you can extract all the parameters associated with your studies, including the gender proportion of females that were represented in each studies, the proportion of males represented, the year the study was published, the country is coming from, the methods that were used in pulling, in doing analysis, and all those kind of factors are extracted. So you can use to explore some of these subgroup analysis. So if you can see my plot here, you will see that we have subgroup A, subgroup B. So let's assume subgroup A represent females, subgroup B represent males. Now, each studies may have reported some outcomes analysis. You can see that we have a lot of, normally distributed curves, 1, 2, 3, 4 to the right hand aspect of right hand side, and we have what do you call it, normal distribution 1, 2, 3, 4 also to our left hand side. Now, these are normal distributed curves coming from our individual studies. If we aggregate them and divided this particular overall effect according to female and male, do we see any statistically significant difference? So for example, the effect of COVID on mental health may have been 0.5. For example, if you are using, let's say, standardized mean difference of certain measurable outcomes of it. And now we now compare that what is the standardized mean difference between male and female? Are there statistically significant differences? If there are, then it's very likely that the effect, the overall effect that we had may have been influenced by the fact that there are differences of males and females. So that is an example of the subgroup analysis. We can basically partition our results or analysis between males and females and check how statistically significant are these effects between these subgroup categories. How do we do this? We have mixed effects meta-analysis where we mix the randomness with the fixed effect analysis with it. These are more likely to make sense to people who have been doing hierarchical models. If you have not done hierarchical models before, this may kind of a bit abstract, but I will try as much as possible to make it simple. So for example, let's assume we are dealing with subgroup analysis with, let's say, so recently I'm doing one that has to do with the whole Africa. So I have to conduct subgroup analysis with countries. However, I was only able to, all the results that all the papers that were eligible were coming from only 10 countries. So in that way, I'm only representing 10 countries out of the 55 countries in Africa. So if I was going to do subgroup analysis with countries, should I assume that the 10 are just the truth, or they are only representative of many? Then that is where the randomness versus fixed effect is coming in. If I'm dealing with countries, then I know that there are 55 countries where I'm working with only 10 of them. So I have to use random effect, such that I'm going to estimate some inferential values that are not the overall, but an inference. So I'm going to use 10 countries to make inference of 55 countries. In that way, I have to check for the, what do you call it? The variability. If the variability isn't that large, then I can make inference about what is happening at Africa level. However, if I was assuming, if for example, my studies or my meta-analysis that is ongoing, I ended up getting 50 out of 55 that was represented in my studies. For example, I got, let's say 50 studies, 50 countries represented out of 55 countries, sorry. In that way, I can say it isn't meaningful for me to think of it like random effect again. What inference at all am I making? Because at least we have more than 95% of the countries already represented in my studies. So there isn't any way of, I'm already very close to the truth. So there's no way I'm going to make any form of random chance inference again. So I can decide to say that any randomness that I'm going to see is a representative of entire Africa. There isn't any way of using randomness, random effect. So that is why it's very, very good for you to use mixed effect or randomness effect if you're dealing with some of these categories. But there are instances where if we have, for example, studies, if, for example, the females have a lot of females and I have a lot of males. Let's say 7 studies dealing with only males, 8 studies dealing with only females. Am I assuming these studies are also going to be having some form of true randomness between each other? Yes, they may be, but they may be small enough for me to assume so. So I can decide to use fixed effect to pull the mean for each of them, and now use randomness effect to check the statistically significant differences between them. Otherwise, in another way too, I can decide to say, okay, I'm going to assume that it's between males and females. However, we have 7 studies in females, 8 studies in males. Now, I'm going to assume that there are true differences between each studies. And then I'm going to use random effect to pull them, like the one I introduced last time. I'm going to use random effect to pull for females, use random effect to pull for males as well, and now use fixed effect to cross-check the statistically significant difference between them. That is also an example of mixed effect. So if you have not been doing a lot of hierarchical models or multi-level modeling and stuff like that in statistics, this will be a good time for you to go back home, then learn more about it. Because once you understand multi-level analysis or hierarchical models, it's very easy for you to understand how subgroup analysis technically work in meta-regression and meta-analysis. Yes, so this is it all about subgroup analysis. I can move on to meta-regression. So we can say meta-regression is more of like, instead of dealing with comparing 2 or more categories, it's more like dealing with some, the common way we look at it, like multivariate regression models. Look at it that way. We are dealing with multiple regression. So we want to look at what is the proportion of variances in our pool means that can be explained by all the variables I've included. So I want to say, okay, I ended up getting 5%. 5% prevalence of HIV across Africa. That is the mean prevalence. However, the prevalence may range from somewhere 27% in, let's say, Swaziland or Eswatini to as low as 0.1% in, let's say, Morocco or Ghana. This is the true span of the variances. However, this particular variance is what explains how big these variances are. What explains it? Is it because of the country the study is coming from? Is it because of how poor the people are in that country? Is it because of the people that were even represented in the studies? Is it because most of the people are males or females? Is it because we have some form of continuous aspect like age? Is it because of height? Is it because of most of these factors? So we want to look at the cumulative effect of all these factors. How much cumulatively can they explain the total variance that we are observing here? If you end up realizing that, okay, the prevalence is 5% in Africa, however, the variance could be somewhere as long as 27%. However, considering 5 or 6 factors explain 90% of the variances in HIV, already you have done something very significant for the health community. You have been able to tell us that overall Africa, these are the 3 or 4 most important factors that we have to look at anytime we're looking about HIV prevalence across Africa. And this is very reliable because we are not doing the inference with one single study. We have combined all studies together. So everything that we are getting is very easy to generalize to the entire African continent than just using one study to do the regression analysis. That's an example of how these things are done. And then we just demonstrate it. So you can see P hat is equal to sum theta plus beta plus xk plus ek plus some other random. So we have two random errors here. If you were dealing with one single study, like I'm doing one study from, let's say, Ibana state, like impact of COVID-19 on mental health in just one study, like an individual person without meta-regression or meta-analysis in particular, then I'm going to examine only EK, which is the random chance by sample errors, which doesn't include the last aspect of it. I don't know that particular sign, what it means, but we have 2 errors here when we are doing meta analysis. But if you're dealing with one single study, we have only one source of error. So just think of these things as almost similar to the way we do our multiple regression analysis, but we have 2 sources of errors here. And then you can see the chart here. There's something that looks more like a standard scatter plot chart, like X and Y. And you can see there is a line where we have superimposed on it some normally distributed curves This is example that we talk about maximum likelihood test. If we're dealing with more of ordinary least squares, we would basically see points that are distributed all across, and we'll only be adjusting the line to see where the line best fit the data. And then we can model our analysis. However, with this, we are basically fitting more of like multiple multivariate distribution around our line. So every portion, so we segment all our data points along the line into singular portions, and each portion will fit a line to see how it obeys this particular maximum likelihood ratio. Because maximum likelihood, we are assuming that our data is coming from normal distribution. So we can fit multiple, like thousands of, simulations at every single division step, and then calculate which one is best showing normally distributed, and we'll pick that one. We'll do that for all the step divisions along the line, and that becomes our best fit for the relationship between X and Y. The X can represent your predictor variable, Y can represent what your meta-analysis values are. And then you move on. We can also do categorical predictors like male, female, just that you have to specify it. If it's male, don't use the raw spellings. Use, if it's male 1, if it's female 0, or male 1, female 2. Use those ones so that it can differentiate. You can use one as a reference value and then give you some results. And then I can move on to, have you all followed carefully with what I've demonstrated? If you can indicate yes. Okay, very good. All right, so I am going on to do a bit of demonstration. So I'll stop sharing this screen and then move on to the other one. All right. How do I stop this? New screen. All right. I'm sharing. Can you all see my screen now? Okay. Tell me if you see clearly. Okay. All right. All right. Very good. So I am going to, if you have used R before, this is a very open source. You don't have to pay for any money. Just go and download the R software and download the R Studio, which is like the IDE, the integrated development environment, where you can do all your coding and then get your results done. So here we have some packages we need to download. We call one dmeta, tidyverse, and a meta. The tidyverse is just used for manipulating data. It's not necessarily only related to meta-analysis. It's related to all statistical analysis. It's used for correcting data, manipulating data, changing rows into columns to rows, all kinds of manipulations that you want to do with your data. You can go ahead with the tidyverse. And then once we have installed all these things, install.packages, then this is a simple code, indicate the name of the code in quotation mark, then run to just give you your code. Then I have already installed all these. And then once you have installed all these, basically just indicate library, just type library and then put the name of the package there and then run. It will generate, it will now import all the packages into your IDE or your RStudio, and it's ready to go. So here, per simple analysis, what I'm trying to do here is understanding the blood lead levels in children across the entire Africa. So I'm looking at what is the amount of lead content in the blood of children, because we know lead is very critical, heavy, toxic metal. Rotate your mobile device if you are using mobile phone device. Okay. All right. So if a child is exposed to like high amount of lead or even small amount of lead, the lead may be responsible for blocking calcium signaling in the brain, or sometimes even dislodge the synapses, and then it pull away the synapses to each other end. So they instead repel each other instead of coming together. And those of you who have done a little bit of brain and all those kind of mental issues or central nervous systems and stuff like that, you come to appreciate that there are some synapses. The more the synapses touch against each other at that point, the more likely we can have neurotransmitters going from one end of the brain to the other. But if the child is exposed to this particular lead, the lead can deceive the structure of the calcium, then kick them away, then take charge, and then begins to destroy some of these signaling. Then the child becomes increasingly dumb with time, becomes cognitively declined. The child may get to a point that it becomes irreversible. And most of the times, they are irreversible. We still don't have drug that cure a child that has gone through lead poisoning. We still don't have the drugs yet. Scientists are so trying as much as possible. So that is one of the example of, I'm going to use to demonstrate to you. So we have our meta package like MetaMean. MetaMean is a package in R used for pooling means of certain things. For example, the mean age or the mean height, provided you just wanted to know the mean height of women across Africa. You can use the MetaMean. Or you want to look at the mean amount of something, I don't know, or mean temperature across different areas, you can still use that. So I indicate my MetaMean, I indicate my values here. So these are the mean in my Excel values. The PB mean are just the mean in the individual studies that I extracted, the raw means. And these are the SD representing the standard deviation. And we have N, the small N represent the sample size of the study. And I have my study lab. A state lab is just like a function in also R that is used for specifying the study. So if I have a particular column about study name like Ama et al. Or Kofi et al., then you can use that particular state lab as the function and then specify the column that represent that particular reference. And then we have our data that represent the name of your CSV file. Then we can decide to say SM, which is used for doing the mean, the log of the mean. We can use mean, but sometimes we just need to make some transformations because we know if I'm dealing with, for example, lead, we know lead normally come from a distribution, or most of the chemicals are coming from a distribution of geometric means, not arithmetic means. If you're going to read further about the differences between arithmetic means and geometric means, it's fine. But normally we are going to have non-normal distributed, more like curve, like skewed data. So we use SM as a function to transform. So we are saying that apply MNL. MNL is a function in R as well. That is also telling the meta-analysis package that, okay, if you're going to pull the means, make sure you transform them all before to a log distribution before. Then I'm going to say, okay, pull for me fixed effect values like I indicated earlier. Pull for me the mean for fixed effect and pull for me for a random. And then make sure, the last time I was talking about tau squared, the tau values and all that. Get me this Del-Simonian lead model. That's my mention about it. It's represented as DL in meta-analysis in R, just DL. And then there are also other ways of correcting for the standard, the confidence intervals, especially you have extreme variances in your mean or extreme sample size differences. You can decide to correct the standard, the confidence intervals. I didn't, so I decided to put false. If either you type the false F or you add the full false, like HKL, then you type false, or you just leave it as F. Then the title, I can decide to say I'm giving a title, blood lead levels. Then I can decide to say I'm going with summary. And then once you click here, I can decide to say I'm highlighting all this here, and then I can click run. Oh, participant who is seeing this recording? Okay, so I can decide to run. Are you all seeing my screen? Are you all seeing the screen? Very good. Very good. Very good. Thank you. All right. So once I have run it, then you can see in my console, it has indicated that it has run because all of them are indicated in green, blue, sorry. Then I can decide to say summary, just type summary. So I can divide and then summary. This is just common sense programming language, not like difficult ones. So BBL, that is the model that I developed. Then I click run. Then can you all see this? Yes. So Okay, somebody wants to see the structure of the data. I'm coming. Okay, I'm coming. I can show you the structure here. Okay. All right. Let me. Are you all seeing? All right. So you can see the structure of the data now. If you are seeing, you can see yes, fine. Then you have the study here, one column. You have the year of the study, the analytical method it was used, whether it's graphite, finance, atomic absorption, spectrometries, whether you use different aspects of lead care or these particular techniques for analyzing them, or the sub-region, whether it's West Africa, East Africa, whatever is coming from, the country, the location specifically, then the setting, whether the study is a population level or whether it was getting like hazardous site, the mean of the raw studies that was reported, the mean values, whether, what is the standard deviation of the mean, the sample size of the study, whether we also are also extracted for whether they reported for mean, male or female. We have like other aspect of sampling design and align condition, whether the sample, those people that were included in the studies, whether the children were having some already underlying healthcare condition or not, because sometimes it can also bias our studies. And then the journal, that type it was coming from, the Gini index of the country represent the income inequality, age, study region, whether the study was conducted after 2006 before 2006. This was very important as most African countries were beginning to ban lead in petrol and gasoline after 2006. So very important reference here. And whether the method of drawing the blood, like whether they use venous blood draw or some form of finger prick or some form of other things like that. The exposure, whether exposure was identified, all those kind of factors. These are the structure of the data. So it's a very large database that you need to. So make sure if you are doing a meta-analysis, your data is very, very important. Very, very important. And I can move on to our destination. Yeah, don't worry. This is just a demonstration. Later on, if you can reach out personally, and then I have time, I can assist you in understanding some of these nuances. All right. So when I click run here, then I get it. I get the results. So you can see this is the results. Here I have Adimuyiwa Eto from Nigeria. And then the mean blood levels are 362 microgram per liter, sorry. And I have my confidence interval from 327 to 400. And then whether it is using a common effect or random effect weight. So it's assigning some weight to the studies. So I'm doing that for all the individual studies until they are done. And I come, okay, the number of studies here, K, which is the degree of freedoms, is 75, K minus 1. Then I have observations, which is the sample size, like all the people combined. We have 14,842 people that were represented in this study. So it's good enough for generalizing to the entire Africa. Somehow, yeah, better than using individual studies for decision making. Then we have the randomness effect. The random effect gives us 100.5 microgram per liters. The common effect, which is the fixed effect, is giving us 88.73. This, the fixed effect, is saying that there isn't statistically significant differences between studies. There isn't statistically, like studies are coming from homogeneous populations. So all Africans are one people, one gender, one everything. And the differences that may exist is going to come from some sample size. This is a very wrong idea, but we still pull it anyway, just for demonstrate or just to see that this is what it means. And you see the confidence intervals ranges from 88 to 89. Very small confidence because the error is coming from only one source. So the confidence intervals is very, very slight. But the randomness effect, we have added additional error, which is the true variances between studies. So sample size differences, and then true differences between studies. And then we realized that it gives us a mean of 100, but the confidence intervals is now huge, from 86 to 117. And then we have like tau squared, which is a measure of the variance between the studies, which is more like 0.4 microgram per deciliters. That is the variance that we are expecting here. And that is the confidence interval from 0.4 to 0.88, which is also very large. And then the tau, which is the standard deviation, when you square it, you end up getting the tau, which is the true variance, which is like the true variance across Africa, if you understand it that way. And then the I squared is 99.8, very large. What this one simply is saying is the proportion of variances attributable to the true differences between studies is 99%. So which means that the differences that we are observing between values is not because of sample size. It's because of true variances, true differences between studies. In that way, it wasn't even meaningful. If I mistakenly reported common effect model means, I may have misled almost the whole public. That is why randomness effect was also cool, just when it has confirmed here. Test of heterogeneity. There are statistically significant differences between studies. I last mentioned about Q test, the Q test, which is here, 37,998.68. Degree of freedom, 75. I once mentioned it, 76 minus 1. And then a p-value of 0, which means 0.000000. I don't know. So which means that there are statistically significant variances in our studies. And we need to explore where the significant differences are coming from, where the subgroup analysis and all those things may be necessary. Then I can decide to say I'm going to do publication biases. It's also very simple in R. Just indicate the function. Meta bias is the function in R. Just write it, meta bias. Input the model that you run. Then meta bias method. I'm going to use linear regression method like linreg. Then you can run your analysis. And then if are you seeing this? Are you all seeing that? Like what I just ran? If you did, just indicate yes. So I'm aware. All right, very good. So you can see that is the title. We have review, blood levels, linear regression test of funnel asymmetry. It's indicated clearly. Test results, t-value 1.18, degree of freedom 74. P-value less than 0, more than 0.05. And I'm already, if you remember clearly, I demonstrated with a theoretical explanation. If you have p-value more than 0.05, it means you don't have significant asymmetry. You don't have significant asymmetry. And that is the issue. And then the bigger the p-value, then the more likely symmetry becomes. The lesser the p-value, the less symmetric it becomes. So in this case, you could see that the p-value is 24%. So we have 24% chance that we have observed this in randomly, which simply says that there isn't any proof, or there isn't enough evidence to show that there is publication bias there. So I can still report my study without any problem. And you can see here sample estimate. We have the meta bias, which is here. This is how much different this is how much different, which is 4.36. This is how much different our distance is from 0. So if you decided there were no differences in like our study errors were at the maximum, in that case there were no precision at all in the meta-analysis that we're doing. Like let's say precision was almost 100% or 1000%. Like, sorry, what do we expect this thing to be? 5 point something. And how significantly different is the intercept from the mean? We are saying that 4.36 away from the mean, which is not too far, especially because we have the meta mean to be 5 point something, the intercept to be 4.36. So there isn't any statistically significant differences between this and then 0. So in that case, our p-value is 0.24, which is more than 0.05. And just a proof that there isn't any statistically significant evidence to show that there is publication bias in our studies. All right. Okay. Now we can go in and then plot it. We can also, doing the publication, the funnel plot isn't also difficult thing. Simply type in your funnel plot or funnel meta, then put in your model you developed earlier. Then click run, and then you can get it. So let me delete this one first and redo it so that everybody is seeing it. All right. All right, so once I highlight this, I can run, and then you see it come. If you see it, indicate yes, and let me see. If you saw the plot drawn, please indicate yes. All right, very good. You all seeing it, very good. All right, so this is the plot asymmetry. So you can see that we don't have a lot of, even though you can see more small, like kind of a little bit, but it isn't obviously clear that it is heavily to the right or heavily to the left. We don't see all those ones like indicated that well. And you see that most of the high precision one, like less standard errors, tend to cluster at the top. And once you come to the down, then the standard errors becomes to like the high variances ranging from 1 all the way to 7. So you see that we have represented both small effect studies with large standard errors and very long variances, as well as big sample sizes with less standard errors and then very tighter confidence bound. The reason why you are seeing the funnel plot not wide as the way I showed in the slide before is here we are dealing with means. So they are using 50% and then building the confidence around that 50%. That is why. If we had given a relaxed form of it, that it ranges from 2 all the way to, let's say, 6, and then build the confidence or the funnel around that, you would have seen that most points would have fallen within this particular bound. So don't be deceived by the small restricted funnel you are seeing here. In most studies, you're going to see very large ones, especially if you're dealing with relative risk measurement instead of means or proportions. All right, so this is a clear demonstration of the, I'm not going to do the forest meta to do the meta analysis like the funnel plot. I'm not going to do that because Leonard is going to handle that sometime. So I'm leaving that for now. Then I'm going to do like subgroup analysis. I'm going to say that, okay, update my meta. So update meta is also a function in meta regression. So instead of retyping the whole code again and then specifying your region, you can simply enter the update meta and then put into bracket your resource, your model that you produce, and the subgroup as a function. And in the subgroup, what are you going to run your subgroup on? I'm going to do the subgroup on subregion, whether the study is coming from West Africa, East Africa, North Africa, wherever it's coming from. And I'm going to say that the tau common F, which means that I'm not going to use fixed effect in pooling my tau squared or our true variances. I'm going to use random effect. Why am I using random effect? Because I only have 10 countries represented here. So I'm going to use 10 countries to make inference of 55 countries. So it doesn't make sense to me to use fixed effect to say that the 10%, the 10 countries are at all the number of countries we have in Africa. No, that is false. So I'm trying to say that, okay, it is false. So use tau common to be false, and then use tau random to be true. That is all this one means. Then I can run this particular code. And then simply say, click summary, and then you run it. Do you all see it? Do you all see the results now here? If you do, say yes. I can't, those who are asking for the script, I can only share with you the raw script without because the data is very, confidential data. We can't share it. for now, since the study isn't yet published. So we can't share it. We can probably give you, like, after this, I can probably give you like rough code, and then you can generate your own synthetic data, or if you have data, you can try it on. But I can't give you this data actually. All right, so if you are seeing it, very fine. So you could see that the subgroup, which is equal to West Africa, have a mean of 1.14 microgram per liters, with confidence intervals 84 to 239, which is very large. And we have 15 studies from Africa, from West Africa. Then we come to, and then most of them are coming from because of Nigeria. To be frank here, most Nigeria is, especially the areas around Zamfara and Co. They do mining there. And because of that, the area is extremely polluted. And then if you never read before, around 2010, there were outbreak of some of this lead poisoning, and over 400 children died instantly. So it's very polluted. And I think that is where most of why the confidence intervals is very huge, because that area was reported very high amount. And we have East Africa, 7 studies coming from there, and in a mean of 61 point something. And then the South Africa, 33 studies with 102. And we have North Africa, 14 studies, 86. And we have Central Africa, 94 point something. So here should have even given you already a raw picture of the subgroup and how it is working. So we are basically partitioning, or we are basically modeling the mean effect or the mean pool effect across multiple levels of multiple regions or multiple categories. And then calculating the confidence intervals and the tau squared and all that. Very interesting. And now you can now test what is statistically significant difference between these particular Africa, West Africa, and all those. What is statistically significant difference between them? And here we have it. The Q, which is the Q test of 19.72, degree of freedoms 4. The degree of freedoms here now doesn't represent the individual states, but now the sub-regions that is coming from. We have 5 sub-regions, so the degree of freedoms is going to be 5 minus 1, so which is 4. Now we have p-value of 0.0006, which is significantly less than 0.05. In that way, we can conclude that there is statistically significant difference between studies when it comes to lead levels. So we can say that, okay, West Africa is the most polluted region in terms of lead contamination, followed by South Africa, followed by Central Africa, followed by North Africa, and lastly, East Africa. So we could basically conclude that East Africa is the less polluted of all Africa. Still very tentative, but we can still make that inference. Are we all understanding the proceedings? Very good. Assume you all understand it. So I can now go on to the meta regression, just run an example of meta regression quickly, and then we can leave chance for questions. Going on here, very good. So I have my meta reg. So in R2, simply type in meta reg as the function and input your model. Now, tilde is normally what is used for saying, okay, I'm running X and Y. So we have on the right, the blood lead levels representing our Y, and then to our other aspect of it, year plus region plus setting 2 plus setting plus sample size plus Gini index plus age plus after 2006. And then we are saying that the tau square should have been restricted maximum likelihood. So I'm going to use maximum likelihood, but I'm using the restricted maximum likelihood. If you want to understand the statistical analysis of it, if you want to join us, use the statistical analysis of it, probably after this meta-analysis, begins to read more on statistics or take biostatistics course. And they'll introduce you to some of these maximum likelihood or restricted maximum likelihood tests. And then I can decide to say, okay, I'm selecting everything, and then I run it. Now, you can see some errors here. Sometimes some of these errors, it's just showing if you are making some error in your data, not necessarily always the important thing to think about. So once I have run, I can decide to say, okay, summary, give me a summary of my results. And if you can all see very clearly, do you all see clearly now? Do you all see it now? Very good. All right. All right. Now I can decide to say, okay, these are my variables, and these are the estimate. So we can easily say that year is negatively associated with the mean blood lead levels, which means that increasing year, the more likely we increase in year, then the more likely it decreases, which is something very interesting, because that is what we want to expect. We want to see if the effort that governments are making in making sure they clean up environment, whether it's working or not, on general. Because we know that before 2006, our environment was much more polluted, because they used to use tetraethyl lead in petrol, which made sure that the environment was basically contaminated. And then they banned it in 2006. Most of them banned it around 2006. So now we can say that the effect of the lead in gasolines and things are reduced. So we are beginning to see some effect. So as the more than the year we go by, then we see it becomes less and less polluted. Then we have it negative 0.1, and then it's statistically significant. Yeah, which a three, what do you call asterisks, which means statistically significant results. Whether the study is coming from East Africa, West Africa, or blah, 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 all of them weren't that significant. Now, when we come to, what do you call it? And then mind you, we are using the sub-regions here. We are making one of the study as a reference value, as a reference. You can realize that we have West Africa, South Africa, North Africa, East Africa, but we don't have Central Africa. So in this case, Central Africa is used as a reference value. So it means that all the studies in East Africa reference to Central Africa isn't statistically significant. North Africa to Central Africa isn't statistically significant. West Africa to this, so that's exactly what that means. Now, when we come to what do you call it? Population level versus hazardous level. Can we observe statistically significant difference between studies that were conducted in hazardous regions versus those that were conducted across the general population? So you can see that there is statistically significant difference. So as compared to studies that were conducted among the general population, those that were conducted in very hazard specific location has more pollution. That is why they have negative coefficient. And this one is also statistically significant. And we have the same thing for Gini coefficient. Gini coefficient isn't that statistically significant. Yeah, even though we know that countries that are higher, more rich, tend to have less pollution, which is very, very what we expect. Very rich countries should have less environmental pollution than very poor countries. And that is very expected, even though not statistically significant, but it's giving us some results. Age is also very significant. So we are saying that increasing age is associated with decreased pollution, which means that kids that are very low, less, those with very like age 1, 2, 3, and those children with very less age have extremely polluted, blood lead content. And it's very disastrous because biomedically, the more like the younger the child is, the more likely the absorptive nature of his gastrointestinal organs are. So it absorbs a lot of lead into the blood system. So this is something we shouldn't expect at all. But here we have it, which is a very bad news for especially children in Africa. And then we have after 2006. Do we have it? Yes, we have it here. Also being statistically significant, but not 3 asterisks. We can say statistically significant at 0.05. And that is giving us positive coefficient. What does it mean? It simply means that studies, as compared to studies after 2006, those before 2006 were more polluted, which is something that we were expecting. Yeah, because most of countries, including Ghana, banned it around 2006. So it was expected results. Have you all followed carefully what I just did? Have you all followed carefully? And then you follow the explanation carefully. All right, very good. So this is the end of what we're doing today. And I hope you all enjoyed the demonstration and the quick explanation. And then, yes, to some extent, yeah. This is that, like the last time I said, you can be an expert by just attending one webinar. So some of these will be organized probably repeatedly as at when I become free, because I'm also a graduate student. So as at when I become free, I can have a talk with Fortune, and we can repeat ourselves again. We keep repeating until most of you have understood it, how we do it. All right, thank you very much. And then now I think we have time for this Fortune. What do you call it? Who is moderating it? Please, moderator, can you take over and make sure people begin to ask questions?
All right. Thank you so much. We have some questions. We have someone here.
We can't hear you. I think your network is there.
Yes. Thank you. Thank you. Thank you very much for the opportunity. Thanks for the presentation. Very interesting. I have a few questions. I don't know if you would want to take them one by one, or maybe I just ask all of them and then you can address.
Yeah, sure. You can ask.
Okay, so I'll just make them brief. I missed the early part of the presentation because I had struggles with joining the link. But I got to the point where you were explaining what the publication bias was. And you did mention that it was the probability that the study will be published depending on the results.
Yes.
So I wanted to understand the intuition, because I know that most researchers, when they conduct their study and they don't find significant results, they don't even publish it in the first place. So when you do a systematic review,
yes,
or if you do this systematic review to get this data, all those studies are actually left out because even the researchers themselves do not even publish it in the first place. And so yes, I'm trying to get the intuition behind using just the data that is published to infer on the publication bias, given that some of those information is not collected by your study.
Yes. Yes.
So that's the first question. My second question has to do with the subgroup analysis. That you gave you explained that you want to perform the subgroup analysis for studies that probably, and you use the example of gender, having only males, and then versus maybe having only females. So you group the analysis. And I'm thinking, what of studies that has information about both? How do you deal with that? So it's the same study, but then there is data, maybe the analysis is, you have data for the males and then data for the females for the same study. How do you deal with that? And in one of in the slides explaining the meta regression, you indicated two random effects. I think one was eta k and psi k or so. And then you said they were random variables. I'm just a bit curious that these two random variables are of the same level. So the subscripts are both kk. And I'm wondering if you will not face any identifiability issue, because then the model would be confused as to which of these two random effects, which one belongs to which. So are there not issues of identifiability, or is there a problem with the model specification? Okay. And my next question, in your data that you shared, so the meta-analysis that you run, you were using the standard deviation. I know that most research work, when they report their study, they report the estimates and the standard errors. So you may find the studies are reporting standard errors, and the requirement for this is that you need a standard deviation. If in the absence of that, can you replace that with a standard error, or what do you have? How do you deal with when only standard errors are reported for the study and not the standard deviation? And then my final question, on the subgroup analysis again, I was wondering, if I do a meta regression where only the subgroup is used as the independent variable, will it give me the same results as the group-based analysis? Can I use, because it's just controlling for only the subgroup analysis? Is it the same? Is the intuition the same as me doing just the subgroup analysis on the subregion? versus me just doing a meta regression with only the subgroup as my independent variable. Thank you. Sorry for the many questions, but I'm trying to understand so many things at the same time. Thank you. Over.
So your first question has to deal with what do we call it? What was even your first question again? Hello? DK? All right. So is it somewhere, can you retrace your first question? So
yeah, sorry, I was unmuted. So the first question was relating to the publication bias.
All right, yeah, I get it.
My question was that there are some people who don't publish that are not significant. If they don't get significant results, they don't even publish it. Or sometimes the journals will reject it because they didn't see any significant results.
Yeah, so that is the reason why normally we are trying to use statistical way of making inference. What is the heterogeneous nature of the population that the studies that you have included? That's what matters right here. Because we are seeing, okay, if we have a lot of studies that we're including some small sample studies and then big sample studies, then we can be sure that we didn't do systematic sampling away. And because especially if and also, for example, if it is guided by some hypothesis, for example, like I use proximity to a contaminated site, we expect inverse relationship in this case. So if a meta-analysis is dealing with some of these things, then the hypothesis is already set. Now, if you do your publication biases, how do you see the heterogeneous nature? Do you only see at the top of it, which is where the standard errors are almost equal to 0? You only see all those ones alone, and then at the downside of it, like below, let's say, and somewhere from 1 below, you don't find any study at all. Then that simply means that such particular search you had, you only had studies that included big sample size enough to have generated very low standard errors. In that way, there's that high tendency that you may have left out very small sample studies. Either they were not published or they were published, but you yourself, the researcher, decided not to include them. And then another important thing becomes is you may still even have the same standard errors from small sample studies, but they only favor some aspect of hypothesis alone, like the inverse relationship. So you have aspect of the sample size, unrepresentativeness, as well as bias representation with respect to the expectation of your hypothesis. So you realize that all of them are skewed to the left because the expectation is we always have to find inverse relationship. What if there are other
so if I got you right, so that means that publications that typically some studies with very small sample size will not yield significant results, and so they may not be included. So in your meta-analysis, you may, if you include studies that have small sample size, then they are kind of representing the studies that have been omitted, right?
Exactly. So the amount of
representing I get it now. Thank you.
Yeah. All right. So your second question has to deal with what did you use? What did you even say?
Was the male only the subgroup analysis? You said you want to do analysis for studies that only have males, and then for studies that only had for females. And my question is, there are studies that may have reported for both.
For both,
you may have for both males and females. How do you deal with that?
If you have such an issue, what you have to do is to transpose. So we have like a function in R for like S apply. So I can decide to say if I have two columns, one column representing males, one column representing females, each of them reporting their own different means value for each of them. What I can simply do is make sure I cut one column then also come and add it to the other one. So they are all under the same column, but in that order. So male, 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 up maybe 37. Then female, 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 up to line 14. But all of them are the same studies. And now,
so a study will contribute. So that study will contribute to both the male side and then also in the female side.
Yes, actually, because if you have to, anytime we are dealing even with the pool mean, the pool means we don't normally when we are dealing with the pool mean at first, we don't consider this gender thing. We just pull all of them together, regardless of whether they are males or females, right? Because we have that particular mean that were recorded for both of them. And then those that are recorded separately. So if you pull all these things together, it means that this is like a pool mean from both female and males. And if, for example, you are dealing with studies that necessarily don't report the average of the two, and you have them separately, then the best normally I would do is to make sure that I transpose them. So instead of them being two columns, I can transpose them into one column. And then I can, fill in all the row or one of the column with studies. Let's say Amma Eto are up to probably number 14. However, the values for the row, for the means, are going to represent males and females. In that way, you can even do simple t-test analysis to see how statistically significant difference are these. So even in a meta-analysis, it handles them the same way. I don't know if you are following the explanation.
Yeah, it's clear. It's clear. Yeah, it's clear. Yeah.
All right. So your third question has to do with what
meta regression specification. So if you go, that one is on the slides.
Okay, good.
The slides on the meta regression.
Yes. So okay, let me share this slide. So looks like, all right. Okay. And now slideshow from beginning. Oh. Where are these?
The meta regression.
Okay.
You just passed it.
Oh, okay, here.
This one,
right.
Yeah. So those two are the board. So you see the index you have there is KK, and you said both of them are random effects.
Yes. So the random effect here represent what are like what do you call it? So we can say the last one, and then the second, like the EK, and then the other. What is even the signal name? I don't know if you know the name.
It is Xi.
The Psi K. Yeah, sorry. The Psi K and then the Eta K. The two of them represent two different things. And then in the meta-analysis, the software automatically calculates two different columns for this. And then the Eta K represents what is the inverse of the variance. And
so then they are not the random effects.
They are a form of random effect, but the issue with the randomness is because we are allowing studies to vary. We are not saying that they are all coming from one single population. If they were coming from one single population, there wasn't any need to quantify for even variance in the first place. So we are assuming.
Yes. So why they need for the same indicator? The only thing that has changed is the eta and then the xi.
So and we are saying
if you impose a distribution on them.
No,
then
the issue and the explanation here is the eta here represent. For example, we have a steady A, like steady on one column, then we have the mean on one column, right? Then the eta K is going to be like, okay, for that steady A, what is the inverse of that variance for that one? So we are going to pick, for example, based on the sample size for that particular study, we can easily get the eta K and say that even if there are going to be some variances between studies at all, if we assume variances, is going to be represented by the inverse of the variance, whereby the variance is going to be predicted by the sample size. And then for the particular, the psi k on another column is going to say, okay, now we have that pool mean, which is the theta k, which is the pool mean we have. Now, how does it deviate from the overall pool mean that we had? So if, for example, we have the whole Africa of 5% prevalence, and the study K had, for example, 27, we can easily say 27, 5 minus 27 is the what do you call it? The last K, which is the random, the variance for that one. Whereby the theta K will be represented by, for example, if that study has a sample size of, let's say, 200, and then the variance of, for that particular study reported a variance of, let's say, 2, then we can easily say 1 divided by 2, which is 0.5, represent theta K. So in that way, we have 2 different sources of the error associated one same single study, but 2 different columns. So it's a simple of adding the, what do you call it, eta K to that particular psi K, and then you get the both of them together. I don't know if you are getting it clear.
Yeah, it's not clear. Maybe I can follow up maybe later on, maybe on the side.
Yeah,
or maybe if you can get some reference materials to give me more further explanation.
These are because we believe study K is just one study. It has a particular mean, right? If we assume that all these errors didn't exist, then this particular mean here, which is the theta here, should be equal to that same thing, right? But then we have 2 sources of error. One error is because the study came from a particular sample size that do not represent true reality. It may have been a subset of a population. So it made error in making sure it was making inference about that population. And what is that error? Then we say the standard error becomes that error associated with it. Then we put it there. For example, +2. Then we have the tilde, what do you call it, the psi K. We also say this is the different kinds of error. That did not necessarily only because of the sample size alone, but because there were some real differences between studies. So theta K and theta F may be represented 2 different studies. What is the mean of the 2 of them? Probably the mean of them is 6. But how different is the theta K from the mean of the 2? Probably deviate if the mean of the 2 is 0.6, and then the theta K is just 0.5, then it deviates from it by 0.1. Is that very clear here? Yeah, so those ones are just true variances between 2 studies. So that is an example of the random effect. So the random effect is saying that studies are not coming from the same population. There are various reasons why studies will never be equal. And how do we quantify these variances? Pick the overall.
So for the 2 of them, what distributional assumptions do you use for the random effect?
More of like we are saying these errors should be randomly distributed, normally distributed with mean 0 and the standard deviation 1. Yeah.
So for both of them, could you assume that they are bivariate normal instead of each one being univariate normal?
It depends. I think normally we would say they are univariate because they mostly, these are, for example, think of it this way, like the eta K represent all the errors that are unaccounted in the normal regression model. We are saying these are all errors that are unaccounted for. And simply, if you're doing your normal regression analysis and you're always going to use some normal distribution of certain variables like the error, and then we are saying this error should not be related to your predicted variable, as we assume, then the mean should always be equal to 0 with some standard deviation of 1. I don't know if you are getting that explanation clearly here.
Yeah.
Yes. And then the eta here is not what we know mostly about the traditional regression analysis. It's normally going to be there when you're dealing with, say, hierarchical models or multi-level modeling. But here we are saying something much more different from what the traditional regression is saying. Here we are saying that instead of even the theta K alone, which may likely be because of this random sampling error issues, let's add the 2 differences between theta K and then the overall theta that we calculated for the overall Africa. And then, so we are basically burdening theta K with different source of error. That is not from only the sample size.
Okay, thank you. It looks like people have other questions, so maybe you can just wrap up with the other 2, then the others can ask their question.
Okay. So the last 2 was related to what?
The standard deviation and standard error. If the standard error is reported and you need the standard deviation.
If you have the standard error is always equal to the standard deviation divided by square root of the sample size. So this is the formula for standard error. This is an example of a change in subject. you can do change in subject and you can easily transform it to standard errors, to standard deviation back. So if, for example, I have SE, which is standard error, is equal to standard deviation SD divided by the square root of the norm of the sample size, then I can easily take what do you call it back, like standard error times the square root of my sample size, and I'll get back to my standard deviation. So a simple transformation, and you can get it back.
So that means the sample size must be known. Okay.
Yeah, so if you use the standard sample size, yeah. Yeah. All right. So what is the last one?
The subgroup analysis versus the meta regression with only the one group.
Yes. So if you're using the meta regression, understand that these are using regression analysis assumption. So we are basically saying we are calculating for some coefficient. We are calculating for some coefficient and then saying the relationship between that coefficient and what we predicted. And then we can say, okay, at the end of it, or what is the coefficient 1 minus 1 is plain ones? And we can always get the R squared, which is not something we can get using the subgroup analysis in itself. For subgroup analysis, basically, is what is the mean difference between the two? And are they statistically significantly different or not? That's a sample. That is something more like analysis of variance kind of thing. I don't know if you are getting me correctly.
Yeah, so that is why I'm asking that question, because I know from analysis, if I do an analysis of variance, it's equivalent to just a simple regression with just one independent variable.
Exactly. So if you are dealing with males and females, then basically going to do like, what is the variance between the two of them? It's basically going to quantify that thing. But if I'm doing meta regression, I'm doing multivariate regression here. I'm including both the males and some other form of continuous variable like age together. And normally the result that the meta regression will give me may be different from what the subgroup analysis is giving me. So when I run, you realize that for the meta regression, we didn't even have anything like U-test. It basically gave us.
Thank you very much. I'm okay. Yeah, thanks.
All right, very good. All right. So for the others, if you have questions, you can also post and then get it there. So if somebody asks a question, how can we identify publication bias in published studies? Yes, that's what something I introduced last. I don't know if you didn't meet here, but simply we have you can use a funnel plot. If you have your funnel plot and all the studies are bounded within it, then visually we can say, oh, there isn't any evidence for publication bias. But that one alone is also subjected to visual bias. So we can use Eagles test or Peters test. And then I will share my slides with Fortune. He will share with you. You will see it there. I'm not going to go back to the equations again. I don't know if you understand it again. All right, thank you. Are there others? Are there others? Hello, DK? I shall get the link. Oh, that's all the questions all of you have, right? Hello? Oh. Hello, DK? Oh, he's not there. Hello?
Yes,
I can't hear you. Okay, no more question. All right. So if there are no more questions, we would end it here. And then if there are other times you meet Leonard, and then I'm sure most of the things I've said here is going to be repetitive, apart from plotting your forest plot and stuff like that. Yeah, but it's going to be the same thing like I've presented. Thank you, and then may God be with you all. All right, bye-bye.
Thank you very much.